Hello, welcome to Lecture 31 of Electrical Circuits 1. Today we're going to be talking about sinusoidal steady-state power, or AC power. This is very important because virtually all the power that's delivered worldwide is sinusoidal, at least once it gets to a household type level. So you're going to see this a lot in the future. Now, there are various categories of sinusoidal steady-state power. We call different aspects of this by different names. Instantaneous power is the power we're used to dealing with. P is equal to I times V. Now, ordinarily, that's not easy to deal with, so more often you'll see people talking about average power or real power. This is power that is absorbed by the system. It's dissipated into forms other than electrical. Okay, it's dissipated as heat in resistors. It's used to do mechanical work. Reactive power, on the other hand, our energy storage elements can absorb power and they can release power. Since there's no resistance associated with an ideal capacitor or an ideal inductor, they don't, on average, absorb any power. Any power you give to them, they are perfectly happy to give back to you. That is termed reactive power. Now, these guys here, real and reactive power, can be combined in some sense, and you can look at one entity called complex power. So, this lecture will be introducing all these terms, defining equations used to determine them. From there, we'll go on to something called power factor. We want to deliver power to people as efficiently as we possibly can. Once we've looked at these, we'll see how to increase the efficiency of our power delivery. The power factor will tell us, in a sense, how efficient we are at delivering power to our customer. Related educational materials are in sections 2.9.0 and 2.9.1. Okay, so we're going to be talking about AC power, alternating current, sinusoidal signals. Power is always the product of voltage and current. Lecture 1, we saw that P of T is equal to voltage times current. At any instant in time, if I take the voltage at that time and the current at that time, multiply them together, I will get the power at that time. Now, since we're interested in AC signals or sinusoidal signals, we're going to be looking at cases where V of t and I of t are sinusoids. And specifically, our format for expressing these is going to be V of t is some amplitude, V sub m, times the cosine of omega t plus theta sub v, which is the phase angle associated with voltage. Our current, I of t, is some amplitude I sub m times a cosine of some frequency omega plus theta sub I, which is a phase angle associated with the current. These will be the expressions we are defaulting to for the rest of the next couple of lectures. One thing that's important to keep in mind throughout the remainder of this lecture is that V of t and I of t are interrelated. Okay, I've expressed them as separate expressions, both of which are sinusoids. They have individual amplitudes and individual phase angles. However, they're not entirely independent. Please keep in mind that you're always applying a voltage and a current to some load with, in general, some complex impedance Z sub L. So voltage and current are related by this impedance Z sub L. They're not independent. Voltage is impedance times current, so the amplitude of the voltage, so V sub m, is the amplitude of the current, I sub m times the magnitude of this impedance of the load. Likewise, the phase angle V, theta sub v, is equal to the phase angle of the current, theta sub I, plus whatever phase angle is introduced by this load. So theta v and theta I are not entirely independent. They're set by some load. Now, it's easy to forget that over the course of the next few slides while I'm talking about them as something that looks like essentially independent entities, but keep in mind that they're not entirely independent. Now let's look at our instantaneous power, P of t, in terms of these AC signals. So our time domain definition of power is the instantaneous power That's just P of t is equal to V of t times I of t. If I substitute my previous expressions for sinusoidal voltage and current in for V of t and I of t, I multiply the amplitudes. I get a V sub m times an I sub m times the cosine relationship that expresses the voltage times the cosine relationship that expresses the current. Now, if I do some trigonometry and some algebra on this, I won't go through the details in lecture, I can rearrange this to look like this. I have a V sub m times I sub m over 2 times the cosine of the difference between the phase angles between the voltage and current, cosine theta v minus theta I. Remember, theta v and theta I are just numbers, plus a cosine of twice the frequency plus the sum of the two individual phase angles. This is kind of an important expression, at least from its overall form. You have a DC or a constant part, okay? Since theta v and theta I are both numbers, cosine of this is just a number. This is a number, V sub m times I sub m over 2 is just a number, so the product of this and this term is just a constant. It's a number. You get a DC level out of this, plus some sinusoidally oscillating term, which has an amplitude of V sub m, I sub m over 2, and a frequency of twice the individual frequencies of the voltage and the current. So you get a sinusoidal part as well. So graphically and conceptually, our previous expression for instantaneous power will be plotted kind of like this sinusoidal signal here. It has a DC offset that is 1/2 V sub m I sub m times the cosine of the difference between the voltage and the current waveforms. It's oscillating. That oscillatory component has an amplitude of 1/2 V sub m I sub m. So depending on what theta v minus theta I is, you can adjust how much of this curve is above or below the x-axis. That allows you to give more or less DC power to your supplier. Okay, you'd like this number to be relatively small so that this cosine is 1, and you don't get these little things where you're taking power away from yourself on average. I want to now look at an alternate representation for our instantaneous power. If I take my previous expressions and do some more trigonometry and some more algebra on them, I can take that cosine of 2 omega t plus theta v plus theta I term and decompose that into a pure cosine with no phase angle and a pure sine with no phase angle. If I do that and group terms, I get a v sub m I sub m over 2 times my cosine theta v minus theta I, which is always going to be around, times a 1 plus cosine of 2 omega t. I also end up with a v sub m I sub m over 2 times the sine of theta v minus theta I times a sine of 2 omega t. Now, I can decompose this expression into two parts, one of which is this upper line and the other of which is this lower line. And I can plot each of them individually. This upper line here, the plot looks like this. I have a DC value which multiplies a 1 plus a cosine. This is an elevated cosine. It has this DC value here. It never dips below the time axis. I'm always dissipating power here. On the other hand, if I take a look at this term, it has no DC offset. It's a pure sinusoid. If I average this out, I'm not dissipating any power overall. Any power that I put in gets taken back out again. So conceptually, these are going to correspond to two different types of power for us later on. The first of these is average or real power. This guy, on average, delivers some amount of power to a load. Right? If I integrate this curve, I end up with this DC level. I'm sending an average power to a load. This guy here, if I integrate it, I get 0. I'm not dissipating overall any power with this signal. This guy here is called our reactive power. It's the kind of power curve you'll see associated with capacitors and inductors. Any power you put into them, you get back out again. You don't dissipate anything. This curve here is associated with doing useful work. I can generate light with this average power. I can do mechanical work with this average power. I can convert this average power to heat in a resistor. So keep in mind that we're going to have two different types of power, one of which is associated with conversion of electrical energy to non-electrical energy, the other of which is associated with just trading electrical energy back and forth between itself. Now I want to introduce average power a little bit more rigorously. In general, we aren't terribly interested in the instantaneous power being delivered by a sinusoidal signal. We're more interested in how much power gets absorbed on average. So what we're going to do is calculate an average power from our instantaneous power. The way you calculate an average of a continuous variable is to integrate that variable over some period of time and then divide it by the time period. That's the definition of the average value over this time. If I do this with power, then I end up with my average power, or sometimes called my real power, capital P. Now, in the mathematics, which I won't really do here in lecture, this period is typically taken to be one period of the sinusoidal signal. We're integrating over a period of the sinusoid. We can, if we wish, integrate over multiple periods of the sinusoid. It's generally just convenient to do it over one period. If I do that, and I'm going to default back to my previous graphical argument, I had a sinusoidal signal which had some average or DC level. That was V sub m I sub m over 2 times the cosine of theta v minus theta I. Both of our previous graphs indicated that. So if you do the math, you end up with this. I'm going to argue it on kind of a graphical background. The math is in the written materials. This guy has a special name, as I've mentioned already. I want to emphasize that it's the real power, or the average power. It's the power that's dissipated to any resistive part of your load. It's the power that's converted to mechanical energy. It's something that's exchanged or lost from the electrical side of the world and going to a thermal, a mechanical, some other side of the world. It's being used to do work. The units of this power are watts. That may be a dumb thing to say because units of power are always watts. However, when we start talking about reactive power and complex power, those also will have units of watts, but we're not going to call them watts. Watts are volts times amps. We're going to call those by different names based on that. We will actually call the real power or the average power watts. It's sometimes convenient when talking about power to refer to what are called RMS values. RMS stands for root mean square. They are also sometimes called effective values. The origin of these is that we want to assess the power delivered by different types of time-varying signals. Say we have some arbitrary time-varying signal and some other arbitrary time-varying signal. We'd like to compare those to see how much the two are providing power-wise. We can use RMS values for the two different time-varying signals to get a feeling as to their overall power delivery. So for example, the power delivered to a resistive load, P of t is I squared times R, which is equal to V squared over R, by definition of instantaneous power. What we want to do with our RMS values is find a DC or constant value which delivers the same average power as this time-varying signal. So as I mentioned previously, this value that delivers the same average power will be called the effective value or the RMS value of the signal. And it can be used to compare the power delivery of different types of time-varying signals. Now I want to outline in a little bit more detail how RMS values are created. Recall our average power integral. We integrated P of t, the instantaneous power, over one period and divided by time. If I write P of t as R times I squared of t and plug that into this integral, the R comes out. I end up integrating I squared of t with respect to time over one period, dividing by the period, and multiplying by R. this still gives me my average power in terms of current as a function of time. Likewise, if I write power as v squared over r and plug that into this integral, I can take the r out. I end up integrating v squared of t dt over a period of time t, dividing by that period and multiplying by 1 over r. So I have power expressions in terms of current squared and voltage squared. What I want to do is find an effective DC value of current, for example, where I can say that this power is R times the square of some number. Likewise, I want to say this power is equal to 1 over R times the square of some effective voltage, which is constant. So what I'm going to do is equate this term to this term, and this term to this term, and solve for IEFF and VEFF. If I do that, IEFF, this R cancels with this R. I have to take the square root of this remaining term. I have the square root of 1 over t times the integral of the square of the current with respect to time. Likewise, the effective voltage, this R will cancel with this R. If I take the square root of what's remaining there, the effective voltage is the square root of 1 over t integral of v squared of t dt. Now you can see why this is called root mean square. I'm squaring the values, I'm taking the mean of them. It's a mean squared value. I then take the square root of it, it's a root mean squared value. These expressions are always appropriate for any time varying signal. On the next slide, we'll specifically look at signals that vary sinusoidally. Okay, so just to formalize the words that I said earlier, the definition of RMS values: the effective or RMS value of any signal is equal to the DC value, which provides the same average power to some resistor when the signals are currents or voltages. Now, for a sinusoidal signal with no DC offset, I'm getting very specific here. And both of my previous voltage as a function of time and current as a function of time expressions satisfy this requirement. The power had a DC offset. The individual voltages and currents did not have a DC offset. Don't use these expressions for any signal other than this type of signal. The RMS voltage is equivalent terminology-wise to the effective voltage. You'll see either or both of these. That's equal to the maximum value over the square root of 2. RMS, or effective current, is the maximum value over square root of 2 of the current. So any signal which is sinusoidal with no DC offset, you find the peak value divided by the square root of 2. That gives you your RMS, or your effective value. Average power in terms of RMS values. Remember, power was written as V sub m I sub m over 2 cosine of theta v minus theta sub I. I can factor this 2 into a root 2 times a root 2, and I can separate those out. This is my RMS voltage. This is my RMS current. If I'm finding average power in terms of RMS values, P is equal to just the product of the RMS voltage and the RMS current, still times this cosine of theta v minus theta I. Now I want to introduce two new terms: apparent power and power factor. Previously, we said that the real or average power delivered is the effective or RMS voltage times the effective or RMS current times this cosine of theta sub v minus theta sub I. What we're going to do now is claim that we'll look at this in a slightly different way. We'll consider this to be the product of two things. It's going to be the product of the apparent power, which is this effective voltage times the effective current, and the power factor, which is this cosine of theta sub v minus theta sub I. My apparent power, V effective times I effective, or VRMS times IRMS, is simply in watts. Now we want to differentiate between real or average power and this quantity here, which is apparent power. So we're going to provide this with what appears to be a different set of units. We're going to use units of volts amps, and remember that volts times amps is watts. So the units are not really different from the units of real power, but we're going to express them explicitly as being volt amps. So if we see a number with units of volts amps, or VA, after it, we will interpret that as apparent power and vice versa. Now the power factor is just this cosine of theta V minus theta I term. Since these are in radians, they are unitless. Cosine of any number is unitless, so very obviously the power factor is a unitless number. This is going to be a number between 0 and 1. The cosine is always positive. Remember that cosine is an even function, so the result of a cosine is a positive number regardless of whether the argument is positive or negative. You can't tell from the cosine what the sign of the argument is necessarily. So what we're going to do to preserve the sign of theta sub v minus theta sub I is to add a piece of information to the power factor. We're going to claim that the power factor is either leading or lagging. The leading or lagging terminology denotes whether the current is leading or lagging the voltage. That's going to be important to us later on if we try to correct this value to make our real power closer to our apparent power. So if we say that the power factor is 0.85 leading, that implies that the current is leading the voltage. If the power factor is 0.9 lagging, that means that the current is lagging the voltage. Now let's take a look at the meaning of apparent power and power factor. What do they mean to us? Why do we care about them? Well, power factor is a property of the load. Remember, if we're hooking up our source to some load and providing some current to that, this theta V minus theta I, the phase difference between the voltage and the current, is set by the load, right? It's the phase angle induced by this load, theta Z sub L. So if the load is complex, you get a theta Z sub L that's not 0, and the power delivered to the load is not exactly the same as the power supplied by the generator. So if Z sub L is purely real, this angle is 0, this is 0, cosine of this is 1, and my power factor is 1. So my real power in this case is the same as my apparent power. If this is imaginary, if theta Z sub L is plus or minus 90 degrees, this guy here is 90 degrees, cosine of 90 degrees is 0, my power factor is 0. And I'm getting no average or real power delivered to the load. The reason for that is that your load has become entirely reactive. It's a purely complex thing. It's a capacitor or an inductor. So you can give it power, it'll give that back to you. You can keep cycling this power back and forth between the source and the load, but you're not actually providing the load with anything that it can use to do useful work. You're just trading it stuff back and forth. You're giving it power, then you're taking it back. You're giving it, you're taking it back. This situation, where the power isn't being used to convert to some non-electrical energy, is called reactive power. We'll use that term more officially later on. Now, so far we have roughly 3 or maybe even 4 types of power. We have instantaneous power, which we're not going to use very much for doing power calculations. We have real power. We also have apparent power. We also have a reactive power that I mentioned informally, but I'm not going to introduce it formally just yet. Now, it turns out that those things can all be very conveniently dealt with by introducing a concept called complex power. It's just an easy way of categorizing all these and making sure that they work together correctly. Complex power is just a way to express the relationships between apparent power, real power, and reactive power. It is defined as the effective voltage times the complex conjugate of the effective current. So it is the maximum value of voltage times the complex conjugate of the maximum value of current in phasor form divided by 2. Likewise, in polar form, it's the product of the magnitudes of V effective and I effective at an angle that is the phase difference between the voltage and the current. Now, in rectangular form, this can be represented as S is equal to P plus J times Q. P turns out to be my real power, Q turns out to be my reactive power, S is my complex power. The magnitude of this is going to be my apparent power. So if I write my complex power S in rectangular form as P plus JQ, the magnitude of S is the apparent power. I already said we'll use units of volt amps for that. The real part of S, P, is our average power, or as I mentioned, it's also called our real power. We gave that units of watts. It's the stuff that we're going to use to do useful work. P turns out to be V effective times I effective cosine theta V minus theta I. Now, the imaginary part of S, Q, is called the reactive power. It's given units of volt amps reactive, or VAR. You'll see things expressed as 347 VARs, volt amps reactive. It is the product of V effective and I effective times the sine of theta V minus theta sub I. So now these are all very conveniently placed into one kind of consistent format, which lends itself to a graphical interpretation called a power triangle, which I'll introduce next. Okay, here's my power triangle. These are not phasors, but they're typically represented as arrows in a real imaginary plane. S is my complex power. It has a magnitude that is equal to the apparent power. P is my real power. It is the real part of the complex power S. So P is equal to this magnitude times the cosine of theta V minus theta I. Q is my reactive power. It's shown as being in the direction of the imaginary axis. Its length is the magnitude of S times the sine of theta V minus theta I. So we have a very convenient graphical form in which to present the material on the previous slide. Now let's do an example. For this circuit, we want to find first the average power delivered by the source, or the real power provided by the source, the power absorbed by the resistor and the capacitor individually. We also want to find the apparent and reactive powers delivered by the source, and then finally we'll sketch a power triangle for the powers that the source is delivering. Part A, the first thing we want to do is find the power delivered by the source. We know that power is equal to V sub m times I sub m over 2 times the cosine of theta sub V minus theta sub I. So what we're going to want to do is represent this circuit in phasor form, find the magnitude and phase of the voltage, which is essentially given to us. We also need to find the magnitude and phase of the current leaving the source. So in the frequency domain, this is still a voltage source. It is 100 at an angle of 0 degrees. I have a capacitor with some impedance, and I have a resistor whose impedance is still the 10 ohms that's given. The capacitor's impedance is going to be 1 over j omega c, so it's going to be 1 over j times 2500 times 50 microfarads, which turns out to be minus j8 ohms. Now, the current as a phasor, I, is equal to the voltage as a phasor over the total impedance. So this is just 100 at an angle of 0 degrees over 10 minus j8 ohms. If I do that complex arithmetic, I turns out to be 7.8 at an angle of 38.66 degrees amps. Now I can use this and the fact that voltage is 100 at an angle of 0 degrees in volts in this expression here to determine the power delivered. So this expression, P is equal to 100 times the magnitude of the current, which is 7.8, over 2 times the cosine of 0 degrees minus 38.66 degrees. If I do the math for that, this power turns out to be 305 numerically, and average power has units of watts. Now we want to find the power dissipation associated individually with the resistor and the capacitor. Previously, we wrote our circuit in phasor form representing the voltage as 100 and an angle of 0 degrees as a phasor, and we determined the current coming out of the source, which is 7.8 at an angle of 38.66 degrees in amps. Now we can use this current to determine the power dissipation from the resistor. All of this current is going through this resistor, so the power dissipated by the resistor, the 10 ohm resistor, is just going to be the effective current squared times the resistance. That was essentially the definition of what our RMS value was. Now notice one thing here. This is also equal to the effective current squared times the real part of the impedance. This resistor is the only element in this network with a real impedance, so this and this are identical. If you had a more complicated network with multiple resistors and you wanted to find the total power dissipated by all the resistors, you could find an equivalent impedance and take the real part of that. That would tell you the power delivered to all of the resistors in the circuit. The effective value here is the maximum value, 7.8 over the square root of 2, since these are all pure sinusoids. I square that, multiply it by 10 ohms. This becomes 305 watts. Turns out that the power dissipated by the resistor is the same as the average or the real power delivered by the source. Okay, the real power or the average power is telling you how much power is converted to forms other than electrical. This resistor is heating up. It's converting electrical energy to thermal energy. That's the only place that this electrical power can be dissipated in this circuit. Now let me erase and I'll talk about the capacitor next. The capacitor's power is purely reactive. So the capacitor power I'm going to represent as Q sub C. Q is our symbol for reactive power. I can write that as the RMS value of this current squared times the imaginary part of this impedance. So I squared effective times the imaginary part of Z. This is going to be, again, my 7.8 over square root of 2 squared. The imaginary part of Z I said as an impedance, this was minus J8 ohms. So this is just 8, or rather minus 8. When I do this math, I end up with Q sub C is equal to minus 244. Reactive power is volt amps reactive, VAR. This power isn't really going anywhere. It's not getting dissipated. It's getting sent to this capacitor and then brought back out again. The source and the capacitor are trading this power back and forth. It's not being dissipated. Now we're going to find the apparent power and the reactive power delivered by the source. The apparent power, which is the magnitude of the complex power, is V sub m times I sub m over 2. Previously, we determined the voltage and current phasors out of the source. V sub s as a phasor was 100 at an angle of 0 degrees. I sub s as a phasor is 7.8 at an angle of 38.66 degrees. So magnitude of S, my apparent power, is equal to 7.8 times 100 over 2, which is 391 volt amps. Remember, apparent power has units of volt amps, which fundamentally is the same as watts, but we differentiate it by a special name. The reactive power is the imaginary part of the complex power. So Q is equal to V sub m times I sub m over 2. That's my magnitude of my complex power times the sine of theta sub V minus theta sub I. If I do that math, I end up with 100 times 7.8 over 2 times the sine of 0 degrees minus 38.66 degrees. So the reactive power delivered by the source is equal to minus 244 VARs. It's the same as the reactive power associated with the capacitor. No real surprise there. The power can't go anywhere else. Finally, I want to sketch a power triangle for this circuit. My apparent power was 391 volt amps. My average power was 305 watts, and my reactive power is minus 244 VARs. If I plot these numbers on a real imaginary axis, so real, imaginary, the average power is the distance in the real direction. This is 305 watts. My reactive power is minus 244 volt amps reactive. The hypotenuse of this triangle will be 391. This is 391 volt amps. There is my power triangle. This guy here is going to give me my theta V minus theta I, which is my minus 38.66 degrees, as indicated by the impedance of the load. This concludes lecture 31. In this lecture, we've introduced a lot of new terminology associated with power. We have RMS values or effective values. We've got instantaneous power. We've got average power. We've got real power. We've got the power triangle, we've got complex power, and we've got reactive power. Okay? Next lecture around, we'll get a little bit more practice calculating those things, and we'll also take a look at the power factor, which we've mentioned in this lecture but not used much of. We'll talk about why the power factor is important and what we can do from a design standpoint to improve our power transfer to some load.